All right, let's take a look at problem 7. So in problem 7, we're told to use the Lee-Kesler method to answer the following. Okay, so now remember, when it comes to the Lee-Kesler method, remember this is the same thing as corresponding states theory, specifically three-parameter corresponding states theory. Sometimes they're called generalized correlations. In our textbook, they provide plots, all right, for generalized correlations. In this problem, I'm going to use that second appendix, which I uploaded to Canvas, only because they have tabulated values of the Lee-Kesler table. So in general, the appendix from our book should have everything that we need. That second appendix, this is where it's used for use of the Lee-Kesler method. So now remember, when it comes to the Lee-Kesler method, okay, the idea is that Z is written as Z naught, okay, which is a function of reduced temperature and pressure, plus omega times Z1, where Z1 is a function of the reduced temperature and pressure as well. So the strategy of solving these problems is we first need to look up TC and PC. Okay, once we look up TC and PC, since we're given P and T, we can compute. Well, look up TC, PC, okay, and let me add and omega. Then we can compute TR and PR. And then 3 would be find Z0 and Z1 from tables. So once we have our values of Z0 and Z1, all right, we can then calculate Z. All right, once we have Z, all right, we already know temperature and pressure. We can proceed and should be able to answer both these problems without an issue. Okay. So let's begin. Okay. So what we're given, so we're told that our mass is 2,000 kilograms, okay, and that's 2,000 kilograms of krypton. Our pressure is 110 bars, and temperature is 20 degrees C. And what I'm going to do is, since we're always working in absolute units, so especially when you calculate reduced temperature and pressure, it's imperative that your temperature is in absolute units. So I'm just going to go ahead and convert this to Kelvin. So remember, Kelvin is Celsius plus 273.15. So this would be 293.15 Kelvin. All right. And so in A, okay, we need to find V total. So in order to get V total, the first thing I'm going to do is I'm going to get V. Okay, how am I going to get V? Well, I need to start by getting Z. Okay, so I need to get V, right? And V is going to be found as V is equal to ZRT over P, where I know R, I know T, and I know P. All right, so the trick is to get Z. And then once I have V, then N is going to be V divided by V total. I take that back, it's V total over V, since N times V is V total. And then once I have N, then I can use my molecular weight to get mass. Okay, but let's take this one step at a time. Okay, so I want to get Z. So what I need to do is I need to go to my appendix, and I'll just use this appendix so I can get everything from here, all right, for convenience. And I'm looking for krypton. Krypton, krypton, krypton. Okay, here's krypton here. So krypton, okay, has a molar mass or molecular weight of 83.8. Okay, and I'm going to write down the molar weight just because I'm going to need that to convert from moles to mass. Okay, omega, okay, conveniently for krypton, omega is 0. That tells us that just two-parameter corresponding states theory is enough. the fact that omega is 0 helps us out because we don't even need Z1, right? I could just focus on Z naught, and I can eliminate this term altogether. So there's omega, so let's get TC, and let's get PC. Okay, so for krypton, TC is 209.4 Kelvin. 209.4 Kelvin. And PC is 55.02 bars. 55.0. Come on. 55.02 bars. All right. So now I can go ahead and I can calculate TR, which is T over TC. Now remember, it's imperative when you do this that you're using absolute units. So that's 293.15 Kelvin divided by 209.4. And I need PR. Here, it's absolute pressure, so I just need to make sure they have the same units. So this is 110 divided by 55.02. Okay. And I see that both pressure and temperature are greater than the critical temperature and pressure, so this would correspond to a supercritical fluid. All right, so let's get a new MATLAB script set up so I can save this and share it with you. Okay, so so our temperature, and so let me pop this down. So our temperature, let's just put it in as 293.15 Kelvin. My critical temperature was 209.4. My pressure was 110 bars. My critical pressure was 55.02. Okay, so TR is T divided by TC. PR is P divided by PC. Okay, so let's save this. Okay, and run it. And so I get a reduced temperature of 1.4238. 1.4238. And reduced pressure of 1.9993. 1.9993. Okay. And when we look at the Kesler, I'm hoping that I can just take this to be 2 to make it easy to read data. All right, so I have my reduced temperature and pressure. So now what I'm going to do is back in the appendix, I'm going to scroll down to the Lee Kesler tables. Okay. All right, and so now we have tables for Z naught, and then there's tables for Z1. So in theory here, I only need Z naught. Since omega is 0, I don't need the Z1 term. And so TR is 1.4238, and PR is 1.9993. Okay. So I need to go to the next table. This PR table ends at 1. So I'm going to keep going. Okay. All right. So, in theory, oftentimes when you're using Lee Kesler tables, you need to perform double interpolation because you could need to interpolate with respect to 2 values of, say in this case, reduced pressure, and then 2 values of temperature. But let's see if we can just simplify this and make this a 1D interpolation if necessary. And I'm going to go that route. Okay. So since you look at the Lee Kesler tables, technically it's rounded to 4 decimal places, so we could, I suppose we could do it. Okay. So essentially what needs to happen is my pressure is going to be between 1.5 and 2. Okay. And then if I go to my temperature axis, 1.4238. Okay, so there's 1.4, 1.5. All right, so my value is going to be somewhere in between here. And so, in theory, what you're doing is you first interpolate with one pressure with respect to temperature, then you interpolate with respect to pressure, and then you interpolate between those two interpolated values to try and get your estimate at the middle. So let me write these down. So I've got 1.4 between 1.4 and 1.5. So 0.8256. 0.8649, 0.7753, and 0.8328. Okay, so this is reduced temperature of 1.4. This is 1.5. Then in terms of my columns, this is reduced pressure of 1.5, and here's my reduced pressure of 2. Okay, so I'll use MATLAB to speed the process up, but essentially you could go in either direction, right? But what you could think of is, well, I know that I have a reduced temperature of 1.4238. So what I can first do is, based on my data here to reduce pressure of 1.5, I could interpolate between these 2 points to come up with an estimate of my value at my desired reduced temperature for my reduced pressure of 1.5. I could do the same thing over here where I have a reduced pressure of 2.0. Okay, so I can interpolate defined values here and here for my temperature, desired temperature, 1.4238. Then once I have these two values, okay, both of these obtained by standard interpolation, I can then interpolate between these two and these two pressures to find the value at my desired pressure of 1.9993. So let's take this in steps. Okay, so I'm going to pop MATLAB down. And let's call this just part 1. And so I'm going to interpolate with respect to let's see, I want to interpolate with respect to temperature at that. So I'm going to create a vector, and so it's going to contain, I'm going to interpolate with respect to TR for a PR of 1.5. So I want this column. So 0.8256. 0.8649. And then this other column where I have reduced pressure of 2. Okay, that's 0.7753. 0.8328. Alright, so I'm going to interpolate in both of these columns for my desired reduced temperature of 1.4238. So temperature will be my independent variable and pressure will be my dependent variable. Okay, so I'm going to call this, PR. And so let's do PR, 1.5. So it's going to be interp 1. And I guess I need, So now I need a vector of my reduced temperatures, which is 1.4 and 1.5. Okay, so I'm going to interpolate in that first column. So interp 1. So my x variable will be my reduced temperature. Okay, my y variable would be now my column, which are my values of Z naught when I have a reduced pressure of 1.5, and I want a temperature of TR, okay, which is what I calculated above. I could do the same thing with the other data. So I'm going to interpolate in column 2. Okay. Bam. Okay, let's see. So if I run it, so in the first column, right, this would be 0.8350. This would be 0.7890, right, which seems reasonable. Now I would interpolate with respect to those two values for my desired pressure. All right, so my pressure vector now is just 1.5 and 2. So now my value of Z naught is going to be interp 1. So now I'm going to interpolate with respect to reduced pressure. The values of Z naught are going to be these two values that I just computed. For reduced pressure of PR, value I calculated above. All right, so PR, so this is my vector of reduced pressure, is 1.5 and 2 where I have reference data. Then this is my values of Z naught estimated at these two reduced pressures for my given reduced temperature. And now I want to interpolate and get the value at my actual reduced pressure. So doing so, I get a Z naught of 0.7891. So I get Z, which is equal to Z naught, in this case, is 0.7891. And that seems reasonable, right? We could have rounded and just put ourselves in this column here. So 0.7891, right, is between these two values and closer to the lower bound, which makes sense because my reduced temperature is closer to my lower bound. All right, so I have Z. So I use my Lee-Kesler method and I calculate Z. And now we want to know the volume. Okay, so how do we get the volume? Well, so now that I know Z, I can get the molar volume. So again, PV equals ZRT. So V is going to be equal to ZRT over P. All right, Z is dimensionless. Okay, so P, I'm going to want to convert. Okay, I'm not a big fan of unit conversions, so I want to make sure, so T is already in SI units, it's in Kelvin. R is, okay, so let me just write down everything. So T, all right, we already converted to SI units. That's R 293.15. Okay, our pressure is 110 bars. Okay, where 1 bar is 1 times 10 to the 5 pascals. So I'll just write that as 110 times 10 to the 5 pascals. Okay, and R, right, the only value of R I remember is my molar gas constant of 8.314 joules per mole Kelvin. Okay, note that it is sometimes common in thermodynamics books to multiply this by the molecular weight for specific species to get a species-specific gas constant. Okay, but no need here. All right, so if I use SI units, V is going to have units of meters cubed per mole. Okay, so let's do it. So if I come over here then, so I'm losing track. So then let me call this, okay, so Z is equal to Z naught since omega is 0. Then to get V, okay, we have P, and let me get P, so P in Pascal is going to be P times 1 e to the 5. So let me convert that to pascals. And then V, as we just worked it out, will be, call it Z naught here, times, okay, I need R in SI units. R is 8.314. ZR, T's good, it's in SI units. Okay, and then P in pascals. So ZRT over P. So I get a V of this. So V is 1.7781 times 10 to the negative 4 meters cubed per mole. Okay, now does that make sense? Yeah, and I mean the issue here is P is very big. P is 110 bars, which is 110 times 10 to the 5 pascals. Okay, so I made a new page after. All right, so now that we know V and we know mass, so we have 2,000 kilograms. Okay, so the question is, what is volume? Okay, well, first I'm going to need to determine the number of moles. So I'm given the mass. So the mass is 2,000 kilograms. All right, 2,000 kilograms. Okay, which would be equivalent to 2,000 times 10 to the 3 grams. Right, 1 kilogram is 1,000 grams. So I can just multiply it by 1,000. I have the number of grams. So if I want the number of moles, okay, so N, okay, the number of moles will be equal to the mass, okay, in grams divided by my molecular weight, which is grams per mole. All right, so this would be 2,000 times 10 to the 3 grams divided by molecular weight of 83.8 grams per mole. Okay. So determine the number of moles. So the molecular weight was 83.8. Okay, the mass is 2,000 e to the 3. So the number of moles is mass divided by molar weight. So number of moles is huge, 2.3866. Times 10 to the 4 moles. Okay, great. I have this. So then V total equals N times V, where I have N in moles, V is in meters cubed per mole. So I'll multiply them together. I'm going to get units of meters cubed. So V total is equal to V times N. So my total volume would be 4.2438. So this could be 4.2438 meters cubed. Phew. Okay, so 4.2438 meters cubed. So the volume of our tanks, 4.2438 meters cubed. And that's all part 1, part A. Okay, great. Part B, is it safe to store 2,500 kilograms in the tank at 25 degrees C? Okay, so So before we were at 20 degrees C, now we're at 25 degrees C. We've added more mass, so our mass is increased. And so what we're going to want to calculate then is the pressure. All right. Let me calculate the pressure of this new system, and then determine if that's less than the maximum pressure that it could withstand. So we're given the mass, right? And so the idea in my head is in A, we calculated the total volume of the tank. So from that total volume of the tank, then with this new mass, we can calculate a new molar volume. And so I'll have a new molar volume. I'll have a temperature of 25 degrees C. And then, so in theory, the state of my system is fixed. If I know V and T. And then what I'm going to need to do is calculate P and determine if that P is less than my 180 bar. Okay, so let's see if we get, and actually, oh no, I take it back. I'm going to cheat. So I could do that, and that would make us iterate in the steam table, or in the Lee-Kesler tables. I'm going to put it in reverse, right? What I'm going to instead do is, let's just assume we had our system's at 180 bars at 25 degrees C, because 180 bars is the maximum pressure. So let's just repeat the exercise that we did in the last problem with the new pressure and temperature. Because then what I can do is, now that I know V total, I can calculate the maximum number of moles, or the maximum mass of krypton that could be stored at 25 degrees C and 180 bars, and then see if that's greater than the 2,500 kilograms I want to store. So let me put in reverse, just so that it automates the process. Okay. Otherwise, we'd end up iterating in the steam tables. Okay. So let me do this. Okay, so I am going to, so I'm going to save a copy of this as B, right? And we're going to go through this again. And actually, blasted, looks like my answer for the first one slightly off. My answer to the first one slightly off because I assumed here I had 25 degrees C. I misread. Okay, so to solve this to get my answer, I used 25 degrees C. So that's, my bad. Okay, but that's okay. Okay, so we'll assume we still have the same temperature, but now we're going to have this new pressure. Okay, so the strategy is going to be, is now at 25 degrees C, I know the maximum withstandable pressure is 180 bars. So with those two values, I want to go ahead, assuming the total volume is the same as in A, calculate the number of moles, or the mass of krypton that could be stored in this tank at that maximum pressure, then see if that maximum that it can withstand or can hold is greater than what I desire. Okay. Otherwise, we'd be iterating in our tables. Okay, so in B, so now our pressure is 180 bars. Okay, our temperature is 25 degrees C. Okay, and I apologize, I goofed this up in the first one, but it's okay, or it's just an example problem. So that's 298.15 Kelvin. So we still have, TC, PC, and omega up there. So if I calculate my coordinates, right, my reduced pressure is PC divided by this new pressure, or P divided by PC. And my reduced temperature is T divided by TC. Okay. And so I'm going to try and do is just kind of go through this piece by piece. So my pressure now, so I'll call this part B. So it's going to be pretty similar. 180. So I'm just going to look through the reduced temperature part. Okay. So my reduced temperature is the same, 1.4238. And my reduced pressure is 3.2715. Good. So then I go back to my Lee-Kesler tables. So it should be behind here. So I have a reduced pressure of 3.27. So now I'm going to be between 3 and 5. Reduced pressure is still my 1.4238. So I'm going to be right between here. So 0.7202. 0.7761. Zero 0.82. Okay, and actually I want to write them down here just so. Okay. And I managed to erase the part of that. This was 7202. Okay, so this column corresponds to reduced temperature, or row, reduced temperature of 1.4. Here's reduced temperature of 1.5. This column's reduced pressure of 3 and a reduced pressure of 5. Okay, and so what I'm going to do is first interpolate in each column to get my value here and here, and my desired reduced temperature of 1.4238. And then do the same thing in my second column, and then interpolate with respect to these two values to get the value at my desired reduced pressure of 3.2715. All right. So let me put MATLAB back on top. So try and reuse this as much as possible. Okay, and we can keep things the same. So this is first column, so now it's 0.72. So this is my first column, 0.7887. And 0.7761, my second column. 82. There's my two reduced temperatures. So interpolate. And then my reduced pressures now. All right, it's 3 and 5. So let's interpolate there and get Z naught. So interpolate and I get a Z naught of 0.7433. Again, since omega is 0, Z is equal to Z naught, which is 0.7433. All right, so now I have my Z. Okay, so I have P and I have T. Now I have my Z. So what I'd like to calculate next is the molar volume. Okay, and once I have my molar volume, I can calculate the moles because I know the total volume. And then I want to see if that number of moles that it can hold at that temperature and my maximum pressure is greater than what I want to hold. All right. So now V is going to be ZRT over P. Okay. Where again, I want to make sure I have SI units here. So just redoing what I had before. Okay. So this should all be good. So my pressure in pascals, my pressure times 1 to the 5. There's R. I calculate V. So V now is going to be 1.0236 times 10 to the negative 4 meters cubed per mole. Okay, V total is the same V total. V total is 4.2438 meters cubed. So N is equal to V total over V. Okay, and that'll be equal to, so let me see, so I'm going to deviate slightly. So let's see, do I still have V total in my workspace? No. So what I need to do is I'm going to need to define V total. V total is 4.2438. 4.2438. So then N is V total divided by V. All right, so I can get 4.1458 4.1458 times 10 to the 4 moles. Okay, now let's convert that to mass. So the mass will be my molecular weight, or molar mass, times my moles. Okay. So I've got molar weight here. So remember, molar weight is grams per mole. So I multiply that by moles. So my mass is going to be N times my molar weight. So 3.47 for 2 times 10 to the 6, and that's going to be grams? Yeah. Okay, so if I convert that to kilograms, so the conversion factor is 1,000, I'm 3.47 for 2 times 10 to the 3 kilograms, or 1, 2, 3. So mass would be 3,474.2 kilograms. Okay, so this is my max mass that the tank can hold at 25 degrees C. Okay, and again, my total volume is assuming I had 25 degrees C in part A, which is slightly off. So now we can hold over 3,000 kilograms. We only need to hold 2,500 kilograms, so it's safe, right? So we are safe. Woohoo! All right. Now, the last question is it appropriate, right? This is another difficult question without looking at compressibility graphs. Now, one, we have krypton, so omega is 0, so you expect two-parameter corresponding states theory to work well. So as long as we're in that vapor region, and we're not too far away from the ideal gas equation of state, then we expect the predictions to be fairly reasonable. All right, so we know we're definitely in the vapor phase. We have a supercritical fluid. The Z's we get 0.74 and 0.7891. All right, so they're definitely not, ideal gas. All right, but we are in that vapor region. So we have a vapor phase. We have a simple fluid. We have krypton. So chances are Lee Kesler is reasonable. All right, we have a simple fluid, vapor phase, so it's probably reasonable. Definitely wouldn't use virial equation here. So this is going to be, chances are this would be a fairly large perturbation from that ideal gas state. But Lee Kesler may be reasonable, just given that we have krypton. Okay. So that was a fun problem. Hopefully you enjoyed it. Key in that second problem was just flipping and thinking in reverse, so I didn't have to iterate in the Lee Kesler tables. Hope that helps.